Uh, let's begin with randomized PCA on the wine dataset. First, I import the necessary libraries such as NumPy for numerical computation, Pandas for data manipulation, Matplotlib for plotting, and scikit-learn modules for implementing the algorithms. Then I load the wine dataset from scikit-learn's built-in datasets. This dataset contains chemical analysis results of wines grown in the same region in Italy. To ensure that each feature contributes equally to the analysis, I standardize the features using standard scaler, which scales them to have a mean of 0 and the unit variance. I apply randomized PCA to reduce the dimensionality of the dataset to two principal components. Randomized PCA is efficient for large datasets as it uses a stochastic algorithm to approximate the principal components. Finally, I create a scatter plot of the two principal components color-coded by wine classes. This visualization helps us observe how well the classes are separated in reduced dimensional space. Next, we will explore kernel PCA on synthetic two moons dataset. Uh, I generate a two moons dataset using the make moons function. This dataset simulates a non-linear separable scenario perfect for testing kernel PCA. Again, I standardize the features to prepare them for kernel PCA transformation. Then I implement kernel PCA with RBF kernel to capture the nonlinear structures in the data. The RBF kernel allows us to map the data into a higher dimensional space where it becomes linearly separable. I plot the transformed I plot a transform data to visualize how the two moon shapes have been unfolded and are now more easily separable. Uh, Next, moving on to incremental PCA on the MNIST dataset. I load the MNIST handwritten digits dataset from Keras. This dataset contains 70,000 images of handwritten digits from 0 to 9. I flatten each 28 by 28 images into a 1D array and standardize the features. This step converts the images into a format suitable for PCA. Due to the large size of the dataset, I use incremental PCA which processes data in batches. This approach reduces memory usage and is suitable for large datasets. I create a scatter plot of the first two principal components, coloring each point by its corresponding digits. This visualization helps us see how different digits are distributed in the reduced feature space. Now let's look at factor analysis on the breast cancer dataset. I wrote the breast cancer Wisconsin dataset from scikit-learn, which contains features computed from digitized images of breast masses. I standardize the features to ensure they are on the same scale, which is important for factor analysis. I perform factor analysis to reduce the data to two underlying factors. Factor analyzed model observed variable as linear combination of potential factors, aiming to find latent variables that explain the patterns in the data. I plot the factors in a scatter plot distinguishing between malignant and benign tumors using different colors. This helps in visualizing how well the factors separate the two classes. Next, we'll look into the TSNE with interactive visualization on the fashion niche dataset. I load the fashion niche dataset which contains 70,000 grayscale images of 10 different fashion items. To reduce computation time, I select a subset of 5,000 images using stratified sampling to maintain class balance. I flatten the image into 1D arrays and standardize the feature. I apply TSNE to project the high dimensional data into two dimensions. TSNE is effective at preserving local structures in the data, making it suitable for visualizing high dimensional data set. I map the numeric labels to their corresponding class names such as t-shirt, trouser, etc. for better interpretability. Using Plotly, I created an interactive scatter plot. The plot allows us to hover over points to see the item, zoom in and out, and click on legend items to isolate specific classes. I also incorporated the IP widgets to add a slider that adjusts the perfectly lit parameter of the TSN in real time. This interactivity helps in understanding how the parameter affects the embedding. Through the interactive plot, we can observe that similar fashion items tend to cluster together, indicating that TSN effectively captures the inherent similarities in the data. Now, let's move on to UMAP on the Olivetti faces dataset with interactive visualization as well. I load the Olivetti faces dataset, which contains images of 40 individuals with 10 images each, totaling 400 images. Applying UMAP, I use UMAP to reduce the dimensionality to two components. UMAP is known for preserving both local and global structures in the data. I generate an interactive plotly scatter graph coloring each point by the person's ID. This helps in visualizing how images of the same person cluster together. Uh, now the isomap on Swiss roll dataset. I create a synthetic Swiss roll dataset using make Swiss roll, which generates a 3D dataset that lies on a rolled up 2D manifold. I apply isomap to reduce the data to two dimensions. Isomap preserves geodesic distance, effectively unfolding the Swiss roll into a flat 2D representation. I, I plot the transform data to visualize how isomap has unrolled the Swiss roll, revealing its intrinsic 2D structure. The visualization shows that isomap successfully recovers the underlying manifold as points that were closed in the original manifold remains closed in the reduced space. Next, it's a locally linear embedding on the S-curve dataset. I generate an S-curve dataset using make S-curve, which is another 3D dataset lying on a 2D manifold. I apply locally linear embeddings to reduce the data to two dimensions. LLE aims to preserve local neighborhood relationships during the dimensional reduction. I create a scatter plot of the reduced data. The plot shows how LLE unfolds the S-curve, mapping it into a flat 2D space. The result indicates that LLE effectively captures the local structures of the data, successfully unfolding the manifolds. Multi-dimensional scaling on the iris dataset. I load the iris dataset, which contains measurement of sepal length, sepal width, petal length, and petal width for three species in iris flowers. I standardize the features to ensure that each contributes equally to the analysis. I use multidimensional scaling to reduce the data to two dimensions by preserving the pairwise distance between data points. Plot the MDS output, coloring the points by species. This helps in visualizing how well MDS separates the different species based on their measurement. Lastly, the autoencoders on the PIMA Indians diabetes dataset. I load the PIMA Indians diabetes dataset, which includes medical diagnostic measurements for predicting diabetes. I standardize the features to prepare them for neural network training. I construct an autoencoder using Keras. The autoencoder has an encoder that compresses the data into a lower dimensional latent space and a decoder that reconstructs the original data. I train the autoencoders on the dataset to learn efficient representation of the data. After training, I extract the encoded representation from the encoder part of the model. I plot the I, I plot the latent space representation coloring the points by diabetes outcomes. This visualization helps in observing how well the autoencoder separates diabetic and non-diabetic causes. So these were all the advanced dimensionality reduction techniques used in the column.